Hi guys, in this video lesson, we're going to be discussing rational functions and their behavior. So this unit within a unit is all about rationals. And a rational function is simply the quotient, which quotient is like a fraction, right? A quotient of two polynomial functions. And so the example they show here, this rational is y equals a polynomial f of x over a polynomial g of x. And that lower polynomial, that denominator, it can't equal 0. And a lot of this chapter is discussing what happens if it does. So here's some examples of rationals. In this first example, we have a constant, special type of linear polynomial over a linear polynomial. We have another rational with a quadratic polynomial over a linear polynomial. And then we have a third with a quadratic polynomial over a cubic polynomial. So this chart here is all about the end behavior for rationals. So what is happening as x is becoming infinitely large or infinitely small? And the cool thing about rational functions is you're going to discover that really it just has to do with those leading terms. And so in the first case, and you'll notice there's 3 of them, if the leading term of each, the numerator and the denominator, have the same degree, then you're always going to have a horizontal asymptote wherever y equals the leading coefficient divided by the leading coefficient. If the denominator dominates, in other words, the degree of the denominator is greater than the degree of the numerator, then we're always going to have a horizontal asymptote at y equals 0. This is the most common type of rational function. And then this last case is, what if the numerator dominates? And this is saying if the degree of the numerator is greater than the degree of the denominator, then you have this end behavior that occurs at this linear function, really. If it's always going to be the leading coefficient over the leading coefficient times x to the degree of the numerator minus the degree of the denominator. And if that numerator, this is a special note, is exactly one more than the degree of the denominator, then we have a slant, or sometimes called oblique, asymptote. Pinch out a little here. Okay, so we're going to decide for each of these, will they have a horizontal asymptote, a slant asymptote, or neither? And if the function has a horizontal asymptote, we're going to actually write its equation. So we're going to do a couple together, and then you're going to try a couple yourself. So in A, the first thing I always look at is make sure it's in standard form, and both the numerator and denominator are in standard form. And then I compare the degrees. In this case, the degree of the numerator and denominator are equivalent, which tells me that I am going to have a horizontal asymptote at y equals 3 over 5. Degree of, leading coefficient of numerator over leading coefficient of denominator. Okay, so then this next one, I look at it, and again, I'm really looking, making sure it's in standard form, and I'm looking at that leading term over the next leading term. And by looking at these, I can tell that that denominator dominates because the degree of the denominator is greater than the degree of the numerator, which tells me that I'm going to have a horizontal asymptote at y equals 0. And if you haven't heard the term horizontal asymptote, or even asymptote at all, it's what a function is approaching as x or y becomes infinitely large. So like, for instance, in this function, what that's telling me is at 3/5, so about here, you're going to have a horizontal asymptote that this function is going to approach at the ends. It might cross in the middle. Could do all kinds of crazy things in the middle, but at the ends, it's going to approach it. We'll talk more about what this means graphically in the sections to come, but like in this one, we have a horizontal asymptote at y equals 0. If you look at that end behavior, the function is approaching 0. Okay, and so then this next one here, again, it's in standard form. So when I compare, I notice that the degree of the numerator is greater than the degree of the denominator. And more specifically, I can tell it's exactly 1 degree greater. 2 is 1 more than 1, right? And so that tells me that I'm going to have a slant asymptote. And we'll talk a little bit more later about how to actually find a slant asymptote, but essentially it's like kind of like a linear function that the end behavior approaches. It's kind of an oddity. So go ahead and look. D, E, and F, and determine, will each of these rational functions have a horizontal asymptote, a slant asymptote, or neither? And if there is a horizontal asymptote, write its equation. Okay, so let's look at D. Degree of the numerator is equal to the degree of the denominator. So I'm going to divide those leading coefficients. I should write each at the front to find that horizontal asymptote. Which I can reduce, so I know there's a horizontal asymptote at a half. So this is 1. The horizontal asymptote is halfway. Okay. In E, the degree of the numerator is less than the degree of the denominator. The degree of the numerator is 0, right? And so because of that, I know that I will have a horizontal asymptote at y equals 0. Just like the one above it. I know it's a little more than y equals 0, but I want you to be able to see it. And then the same thing on this last one. The degree of the numerator is less than the degree of the denominator, and so I have a horizontal asymptote at y equals 0. Okay, next page. Okay, so we want to write some limit statements to describe the end behavior of each of these following rational functions. So if we look at this first rational function, we can compare the leading coefficients, and we notice that these leading coefficients, leading terms have the same degree. So that tells me I can find a horizontal asymptote by dividing those leading coefficients. So what that tells me is if I were to sketch a rational function, and hey, we haven't really sketched any of these yet. Oftentimes you may have done this in Algebra 2, but you can see in these graphs below, these are E and D are examples of what rational functions may look like. That might help you with A, B, and C. So anyways, what this is telling me is that I have a horizontal asymptote at a third, which doesn't tell me much about the inside portion of this function. And if you're curious, you're welcome to graph it in a calculator right now. But what it does tell me is it tells me that as x approaches positive and negative infinity, the end behavior, whether it be like that, or like this, or like that, or like this, either way, I can tell that my horizontal asymptote is 1/3, which tells me the limit as x approaches negative infinity is 1/3, and the limit as x approaches positive infinity is 1/3. Okay, so let's look at B. We look at those leading terms, and looking at those leading terms, we can tell the degree of the numerator is less than the degree of the denominator, which tells me I have a horizontal asymptote at y equals 0, which tells me that just like in that last sketch, that as x becomes infinitely large or infinitely small, the function is, no, that's not going to show very well. The function is approaching 0. Okay, last one. So in this last equation form, when we look at these leading coefficients, we can tell that the degree of the numerator is greater than the degree of the denominator. And I'm going to kind of, I don't know if I can in this screen. If we go back here, remember we talked about how there would be n behavior similar to leading coefficient over leading coefficient times x to the n minus d. And that's coming from this fact. Essentially what you're doing is you're going to look just, you can tell I pinched in on it, you're going to look just at those leading terms and you're going to say, okay, negative, you're going to end up with a slant asymptote, I should say slant asymptote, I'll do it down here, at y equals, and you're really just comparing those first terms. So you're going to be left with negative 3x, because x to the fourth over x to the third simplifies to just x. So what that's telling me is that I'm going to end up having a slant asymptote that looks something like this. And what's happening in the middle is kind of hard for you to see, but what you do know is that as, oh, that didn't sketch very well, is that as x gets really big or really small, the function is approaching positive or negative infinity. And if you don't feel great about that sketch I just made, let me tell you, as these next couple lessons unfold, they all are giving you information that helps you grapple more with how to build a graph, or sketch a graph really. And those pieces will kind of unfold over the next few lessons. So if you're not quite there, that's okay. Or you can use a graphing calculator till we get there, just to check things out if you're questioning some of the sketches I make. In fact, I even kind of questioned that last one. I would probably have to think about it a little more than I did when I made that sketch. So this one's easier because they're given something graphical. So what you can tell is that as x is becoming smaller and smaller and smaller, the function is approaching 2. So the limit as x approaches negative infinity equals 2. But as x becomes infinitely large, as it's getting larger and larger and larger, the function is also approaching 2. Something very similar. X is getting infinitely small, the function is approaching negative 1. As the limit as x becomes infinitely large, the function is approaching negative 1. So we're really writing the same thing just about twice. Okay, so let's get into slant asymptotes a little bit. So if you ask the calc kids to help you on this, they may sigh a little. This is not their favorite topic, but we'll read the definition and then we'll do some examples. So the definition says, if the degree of the numerator is exactly 1 greater than the degree of the denominator, a rational function will have a slant asymptote that is parallel to the ratio of the leading terms. This is what we just did in example C. So really what you're doing is you're just taking these terms here and you're making a comparison. Okay? And the slant asymptote occurs when it's exactly 1 degree greater. So if the numerator, if its leading term was x to the 8th and the denominator had a leading term with x to the 7th, that would work. We'd have a slant asymptote. So let's look through all of these. So first of all, it says which is going to have a slant asymptote. Well, 1 won't, because when you compare those degrees, it's not 1 greater. 2 won't, because when you compare those degrees, the numerator does not have a degree 1 greater. And 3 won't, because when you compare those degrees, they're 2 greater. Oops. So only 3 has a slant asymptote.